So, okay guys, good afternoon everyone. According to our timetable, we should have another 2 hours on this Friday, right? Yeah. But actually, I'm asking our timetable service to move the 2 hours lecture on this Friday to the revision week before your exam, because I think it's much better. Right? So after the 2 hours today, you can just go through the examples in my previous lectures. And I believe you have some questions. We will do the review just before your exam, and I will leave about 1 hour to answer the questions from you. So I think in that style it could be better. So about the normal teaching, I think today we are going to do the last 2 hours. And in the first hour, I will go through I will go through this teaching material. It's about offshore operation. But actually, when I got the teaching material from Professor Long Bin, I just had some photos like this. So I think in previous years he just told you guys some stories based on the pictures in the slide. But actually, we know that today, if you just go to YouTube, you can see many very good videos to see how to install the offshore structures like that. And previously, I have showed you some videos already. And actually, if you are interested, you can just go to YouTube or go to Google to search something. But in my teaching, I changed something, and I want to use about 10 minutes to go through some projects in our school to let you know what we can do in our school. And I think probably it's better to help you to think about your final year. Sorry, it's not your final year thesis. It's your MSc thesis, because I know some of you probably you don't have any ideas about what you are going to do for your thesis, right? Yes. And you don't know where to go to find your supervisors. So I will show you some projects in this lecture. And then, if we have enough time, I will do a review for previous lectures, and I will leave 2 questions or 2 examples, and you can do some practice after the lectures, and I will answer the questions from you in the revision week. So, here is the outline from the previous teaching materials. You can see that we will see some installation operations for different offshore structures, like the jackets, like the spar, like the hub to launch and the recovery, the ROV. But as I said, it's better to go to YouTube to see some videos. I think it's better to than talking here. Oh, it's a video. Well, I download this one from YouTube to show you an example. And if you just go to the website, you can see some other videos. But because they have copyright, so I don't want to copy all of them to my teaching materials. Just show you an example. Here is installation operation for jacket. So you can see the procedure from the very beginning, but previously they have built all the modules already. So they just combine them together and put in the operation area. And during this procedure, we may have many topics to do, and I think nearly all of them, they are possible to be done in half a year. So I think you can think about it about the hydrodynamics things or the operations like this. And in our school, we have Dr. Yun Chang, Dr. Nian Zong, and they are very good at structure things. And Professor Long Bin is very good in hydrodynamics, as you know. And for floating turbines, we have Dr. Wen Xian, the second lecturer for this module. I think you will see him in next week because you have another 12 hours for this module, right? So if you are interested, in wind turbine or floating turbines, you can talk to him. And my research, currently I'm doing the CFD simulations for multi-phase flow transportation in subsea systems. So if you are interested, you can come to me, we can have a further talk. So from this video, you can see that it's a very typical installation operation. They have some modules and build up in shipyards, and they transport to the area. They put the structures first and put the platforms on that. And of course, after that, they will install some other facilities like the power plant or something like that. So here is the operation for fixed jacket structure, but actually nearly all the operations will follow this procedure. They build up the modules onshore and transport to the location and launch them to the sea water. And after you have the structures, we also need some facilities to put on the platforms to make sure your normal life on that structure is okay, because sometimes you need to stay there for several months. And here is the floating spar, probably with some mooring lines and risers and the water, but from this picture you can't see that. But if in terms of installation, actually it has a very similar procedure like the previous one, like the one for this jacket structure. And well, when we have the structures, like we have a floating spar, we have some fixed structures, but anyway, we need to transport the subsea products from seabed, from the wells to the overwater structure. So it means we need some pipelines for the transportations. But when we install the pipeline systems, we have several approaches. In this slide, I can show you two of them. They are the most typical two. The first one, we call that S-lay, and the second one, we call that J-lay. And probably you know that from other modules. So we also know that if you use different ways to lay down the pipelines, like you can see from the two figures, to the pipeline, they will have different stress features. So it's another very good topic for comparison if you have no idea about what you are going to do. So I think you can think about it. And in our school, we, as you know, we have a cluster room, and we have some very good software to do the simulations. We have MAXsurf and Aviva for ship design. We have CSAM for hydrodynamics things. In CSAM, we have HydroD, we have Deep Sea to do nearly all the things in this area. And I think we can also use OrcaFlex for pipelines analysis. So I think if you have a good idea in this area, I think we will have enough support for you in our classroom. After you have the structures, after you lay down the pipelines, another important issue is to transport the products in the transportation system or in the pipeline systems. Because, for example, from this figure, you can see that in a subsea project, the area could be huge. Like from this case, the pipelines could be nearly 100 kilometers long. So when we do the transportation from the biosphere to the structures over there, we may need a lot of power for the transportation. And because from the seabed, usually we have multi-phase flow. In a good case, we should have oil and gas, but in most cases, we also have water. So it means in the whole system, we have 3 phases: oil, gas, and water. And gas is okay, oil is okay, but actually we don't need water, right? So imagine that if we have a pipeline as long as 100 kilometers and you transport some water from deep sea to floating systems, and you are wasting a lot of power, right? And during this procedure, we also have another big problem that is, we call that slugging, or riser-induced slugging. It's another good topic for simulation, because we always need to know the slugging-induced problems or slugging-induced issues. In some old projects, they use a very big separator on the structure platform. And after they have the 3-phase flow, water, oil, gas, and they separate the products and drain the water again to the open sea. But now in some modern projects, we put a very, very small separator just on seabed, and just after we have the products, we do the separation. We drain the water directly and transport oil and gas to sea surface. So in that case, we can save a lot of energy. And about the design for the separator is another very good topic. And here is my research at this stage, and I'm doing some safety simulations to predict the slugging flow in pipeline and river systems. And from this picture, you can see that today we may have different projects in open sea, and according to different factors like the seabed features or the material properties of the pipelines, we may have different shapes. So if we have different pipelines, we may have different riser-induced slugging or slugging-induced problems, because, for example, if you have a pipeline in this way and you have a pipeline in this way, they will have different slugging features, right? And because in some modern projects, we are going to deep sea, and probably the sea depths or the value for the water depths could be 3,000 to 5,000 meters. It means the vertical riser could be very, very long, and the volume of the slugging part could be huge, right? So it means we need to predict how much of slugging volume we will produce in this project because of this pipeline. And then after that, if you have some very accurate governing equations, you have a good program, you can predict the things going with time. And And in this project, after my simulation, you can see that because of the slugging, we have the pressure fluctuation in the system. And we can see that we have the periodical pressure fluctuations. It means we have the frequencies again, right? Because the water depths could be huge, and it means the static pressure from the slugging could be huge. It means the vibration could be huge, and it's a big problem to the downstream facilities. And because for the horizontal axis is for time, it means we can have the period, right? If we have period, it means we will have a frequency. But to the whole system, we should have a natural frequency, and you know that, right? Like in previous lectures, we can estimate the natural frequency for a floating structure in a way like something like this. But to different designs, we may have different criteria for calculation. Anyway, if in this system, because of this slugging, we have a frequency, and for your system, you have a natural frequency. Now we have the problem, right? Because you need to predict this one, you need to estimate this one, and to make sure they are far away from each other, right? But if you have waves, you have another frequency, if we assume that the wave is a regular wave. So the relationships between the two, or among all the three factors, they should be away from each other, right? Otherwise, you have problems again. So it's another good topic if you are interested. Actually, it's from one of my papers published in this summer, and I went to Korea for a presentation in this July. It was in Busan. If you are interested, you can download this from Google. I think it's already for downloading. And probably you know that we have another lecturer in our school. He's from Thailand, Dr. Narakong. He's very good at VIV problems because in my research, I focused on the internal flow in this system, and I focused on the vibration induced by the internal flow. But Dr. Narakong, he focuses on the VIV vibrations. So if you put some monitors on this pipeline and put it in an open series current, you can see that you still have vibrations, right? And we call that vortex-induced vibration, VIV. So we have another frequency. And then for this system, you have 4 frequencies. We need to make sure they are away from each other. So it's another problem. So actually, you may have many topics in this area. If you are interested, you can go to Dr. Narakong or come to me. And because we have vibrations or pressure fluctuations, we have fatigue issues, right? And in our school, Dr. Yung Chang, and do you know him? The Chinese gentleman. Dr. Yung Chang and Professor Bob Dahl, they are very good at fatigue issues, so you can talk to them. Well, I just talked about the pipeline related issues, but actually when we do the pipeline installation underwater, we need some help from ROV or from AUV, right? Like you can see from this photo, it's an ROV from a local company in North Shields and in West End. It's a very good company in this area. And last year I went to the company and to have a look. They have 3 very, very big underwater machines for Brazil. I think it should be taller than 10 meters because when I just stand there, it's like a transformer. It's really big. And but they also produce and they also design some small machines like this to bury the pipelines to make sure you don't have any vibration problems. If you put some soil on that, it will be fixed, and we can avoid the vibration problems. And of course, we can avoid the wave problems because you don't have any current anymore. So if you are interested in this area, I would like to provide some more information because my wife is working in that company. Yeah. It's the company's name is SMD, and I think many years ago it has a long history, but many years ago it's a company for tractor. But today, because we have oil and gas in North Sea, so they design and produce some underwater machines. And because you know that we have a towing tank in the ground floor, and we can do some experimental studies and investigations. Well, I got 3 pictures from previous investigations carried out by different students. The first one, I think it was before I came here, so I don't know many details about this. But the second one, it was finished by Dr. Simon Benson and a student of mine. It was a Chinese girl in last year for a stage 3 final year project, and she did some towing test for the total resistance for this one. And this is a project funded by SMD. So you can see that the model is very similar like this one because it's just a project for this one. And in Professor Longbin's group, we have a guy from Egypt, I think. He's doing the hydrodynamics analysis for the operations like this. When you put the ROV to the water, you have, if we look at the shape in this way, and you will have lifting facility in this way. And sometimes if the ROV is big, it means your gravity center will be changed, right? So when you have waves, when you have wind, we may have very, very big issues because you don't have enough stability performance. Even you don't have waves, you don't have wind, we still need to do the stability analysis again for the whole system because everything is changed, right? So it's another good topic, and we can do that in our school. So if we look at a project, you may see different devices or different facilities in the whole project, and some of them are very typical, and you can see them in every project. Like, of course, if you are doing drilling, we have some valves, and for each valve, we should have a tree on top of the valve to control the flow rate, to control the the pressure, and sometimes they do the separation for water and oil directly. But of course, we need something to control the flow. And from this picture, it's a very good one. You can see that if we put a tray for each valve, we can combine the flow to some ports like a station, because we don't transport them directly to the structures. Otherwise, it's not very economical. We need to combine them together at a station and to do some processing first, and then after we have some good products, we transport them, because probably the water depth is quite high. If you transport everything, it's not very good. And in a project, if we have this one, we call that subsea manifold. Sometimes it's small, but sometimes it's very, very big. Like in this photo, that's another good photo. You see the red point? It's a car. So from the comparison, you can see the scale of this facility. But not always so big in projects. So if you go to Google, I believe you can see many pictures for different projects at different locations around the world. But sometimes well, different structures, different facilities. But nearly all the projects, in all the projects, they have the facilities, like in this picture, because they have some valves, they have a manifold, and maybe they have some plants to provide you power, to provide you the signal or do signal processing. And apart from the pipeline for transportation, they also have some cables, because you need some facilities to control the pressure, to control the products. So you really need signals, right, for control. You really need power for control, or sometimes you need hydraulic, mechanical things for that. So in this photo, it's a very typical one, and but based on the facilities here, you may have some other things. So don't be surprised if you see other things. So I think we can stop here, because now you have an outline, and then if you are interested, you can, sorry?
With dissertation, if you're doing like a theoretical or modelling one, does it need to be based on a specific case study, or can you just do like a general scenario?
Usually to a good thesis, you need a chapter for your methodology, for your governing equations, but after that, usually you should have some case studies, because you need to explain how to use these theoretical things. Yeah, so I think in that case it's necessary.
So it wouldn't just be based on one scenario, like in a specific one in the title of like a region?
One or more than one, yeah.
Okay.
Yeah. But it depends on the discussion between you and your supervisor, because you need to finalize the final topic, and you need to discuss how to do the whole procedure from the very beginning, and what kind of conclusions you want to make in the very end. So based on that, you can design your structure of your thesis. But for sure, you need some case studies. So if just in terms of offshore installation, I think I can stop here, because they are very general, just to help you to understand some very key points in this area. And in my part, I should have 12 hours for my part, and I think in my part I can stop here because in this area, today it's better to do the jobs by some software, because as you can see from the previous examples, if you want to do some calculations or estimations, we need to simplify many things, and we can only assume that the wave is a regular wave, and you have an expression for the wave surface, and then you can carry out the estimations. And but actually, after you do the estimation, you may find that the result is far away from the result you get from the software, because we have too many simplifications. So I believe in your thesis you will find that it's very attractive to do something in this area. But in my lecture, I think I need to stop because I don't have any more things to tell you. Yeah, and but because we have 2 hours today, so I would like to give you a brief review to my previous lectures, and then after today you can do some practice to the previous calculation examples, and I think it's very good to leave about 2 months for you, and you can do some practice, and then you hold some questions to the revision lead, and we will see each other again. Okay? So I can go to my brief revision. So if you go back to previous lectures, I think you can find that we have only we have only 2 points. The first one is how to estimate the wind force on a structure, and the second one is to estimate the wave force on a structure. And when you do the estimation for wave force, we have estimations for force, we have estimations for the corresponding motion. And for motion, we have heave, we have surge, because we always assume that we have a 2-dimensional problem, so you can only have wave. You can only have heave, and you can only have surge. And if you have a good table from reference books, we have the expression for the motion, and you may have an expression for the potential velocity or velocity potential, right? And based on this expression, you will have velocity, and then you will have acceleration, and then based on them you can estimate the force, and I will go through them. So the first point about wind, actually the estimation is quite simple, and here is a very general expression. We should have the density of air, we should have a good constant, and you should know the projected area facing to the wind, and then obviously you need the speed of wind. For wind speed, we know that if you monitor different points from ground, the profile will be like this. At different heights, you have different wind speeds. So usually we assume that when we talk about wind speed, we use the monitoring point at 10 meters height. Okay. And another thing is, if you put a monitor here and you plot the wind speed with time, it's not like this, right? Sometimes the value is greater, sometimes it's lower. But in estimation, usually we assume that we have a stable wind and the wind speed is the average value, and we call that mean velocity or mean speed. So in estimation, here is the mean wind speed, and we assume that it's stable. And I think you can see this example in previous exam papers, yes, if you download some papers. Here is a very simple case to estimate the wind force on a floating structure. And on this structure, we have two different things. The first one is a tower. It's a porous structure. And the second one is a deck house for accommodation or for something else. But they have different features. So actually, if you follow the rules from API, they should apply different coefficients. And when you estimate the force, you use different areas, right? Because we assume the tower and the structure, we know that they are porous. So you need to use the areas twice, right? In our previous calculation, that's the reason why you can see 40 or 20, I can't remember. But anyway, here is the area facing to wind. Here is the area to me. And when we do the estimations, actually it makes sense to use this area because it's facing to the wind, but actually we also include the side area because we need to think about the friction, right? It's 40, right? 100 is the area for the area facing to wind, and 40 is the area for the side, right? On a side face, yeah. So 100 here is for the area in this side, and another 100 is for this side, right? And 140 is for this side, another 140 is for the other side, right? And I think in your exam question, you will see a table like this if you need. And they are for different things on this structure.
Was this one we're using side of building system?
Sorry?
Was this calculation we're using side of buildings, yeah? Which is 1.9. Could you go back to the table? Was this one we're using CD coefficient?
Yeah, this was
Side of building we're using, yeah? Or beams or what?
For the first part, we use overall projected area of platform, because we have the side, we have the facing side. Right. And for the back halls, is here. It's a building on your structure, and we use 1.5. You can see that in the following page. For the deck house, we don't use the set area, we just use the area here. But if you go to the coefficient, we use 1.5, okay? And you can see that from here, right? And when you use the area, it's here, it's 20 square meters. It's defined by API, so after you have the equation, just follow that, it's fine. And if you follow another rule from ABS, we need to.
Why are you using only that side of the house, of wind side? Why are you using only?
Because the wind is coming from this way, it's acting on this face.
Why you are not using this side?
It's defined by API, I don't know. It's from experiments. Yeah. Because when you follow the rules in most equations, they don't make any sense. They are from experiments. If you follow ABS rules, we need some more information. But when you need that, we need to define the areas for different components. If you need to follow this rule, I will show you some other information, right? So don't be panicked. So if we go to waves, well, we know that we may see some very strange expressions, but all of them I think you can get from the equation table.
This pressure form of dynamics, this is for the, it's different for the deep water.
It's a general form. If for deep water, E will be very big, the value, and the whole term will be 1, right? So that's why when we assume the water is deep, we don't have this term because it's 1. Probably in your calculation, you may think some information are missing, but actually if you have the expression for velocity potential, what you have? if you can find some information like this from the equation table, we will know everything actually. And from the table, you can see that you have u and you have the acceleration du over dx, right? Actually, it's the acceleration in horizontal direction, right? But you don't have v and you don't have dv over d. You don't have them from the table. But actually, after you have the velocity potential, you can get this, because we know that v should be sorry. If we do a differential operation for phi over z, we will have v, and we can just write it down. Am I right?
This is
Right?
acceleration, yeah?
It's velocity. It's velocity.
In your case,
Az should be dv over dt. We do a differential operation for time. So where's time? Right? We can get the information for velocity and for acceleration from velocity potential. From the table, I think you can see that we have the information here, but we don't have the velocity and acceleration in z direction. But actually, we have this. So you should be able to get them. So it's not a problem. And another thing is, after we have the expression for velocity, for acceleration, you can see that, for example, in this expression, we have period, we have frequency. Actually, they are talking about the same thing, right? But when we say something for wave, we don't say wave period is how many seconds or how many minutes, but we always say that the wave frequency is something. So according to the wave definition, we know that frequency is r pi over period, right? So it means here we have we can write the expression for acceleration in this way. We don't have period anymore. And then for deep water, we also know that omega square should be kg. K is the wave number. G is gravity acceleration, right? So actually we can, it's kgh. H is amplitude of the wave. That's the reason why in your example you can see the expression here. Don't be surprised, because we can get that from the velocity potential, right?
Can you repeat that part, please?
Sorry?
How did you change the equation? I mean, in terms of G.
How it became minus, can you explain the difference?
How did you introduce G and
It's for deep water. It's definition.
Okay.
Yeah.
Yes.
Not for deep water, you will leave this one, yes, with the V.
Sorry?
With the frequency, you will leave that one in the formula, which is above that. For the, I mean, shallow water.
For shallow water, we have different expressions, but in the examples in my lecture, we just use the example for deep water.
Yeah,
Because in shallow water, we have some other factors that can't simplify. It's too difficult for cases. Yes. You can do that by programs, but I don't think you can do that by handwriting.
In place of omega, you have substituted kg, but omega square is kg, so it must be root of kg.
I think you are wrong because here is omega over 2, right? And you have omega already, so it's omega square. That's why I just use kg, not kg square root, right?
What is the meaning of H in that equation? Is the wave height?
H?
Yeah.
Can you go to the table?
Yeah, the wave height. So that's the amplitude.
Yeah.
And it's a fixed value because in the example they use 6 meters. 6 meters, sorry.
It depends on the exam. Oh, sorry.
Because in the example it says nothing about the
depends
wave
on
height.
the example.
Okay.
Yeah. Of course, you may have different values.
This one.
And if you're not given H, you assume the left hand meters.
Sorry?
Do you assume that it's not if you're not given it? Because that's a
Question. This, assuming that the body itself weighs is h over lambda and are smaller, do we need to consider this thing also when we're calculating?
Not in this module.
If it's
To make sure you can do the calculations in this module, in every example, they meet the criteria there.
lower than 2
I think so.
in other case, we will use the other one.
You want me?
For example, let's say that the body is lower than 0.5. Waves like that.
The wave height over the length.
Yeah. So if it's, for example, higher than 0.2.
I don't have that case in my module.
One more question regarding this height. When you have semi-submerged object, let's say, and when you're going to calculate the forces, and for this one, and in the area, do we need to, for example, halfway submergency? So are we calculating the height of the submerged plot or total height?
Not total height, because you are doing the interactions between wave and structure, and you a part of your structure acting this way.
Okay.
Yeah.
For the force, you're just calculating which is how.
So, when we do the estimations for the interaction between wave and structure, we actually have three parts. If we divide the force into different categories, the first one is from your table, you have the pressure expression, right? And for that pressure, you have static part and you have dynamic part. When you have motion, it's from the dynamic part. Okay. And we know that if you have acceleration, you have ideal mass. And of course, if you have motion, you have resistance from friction. So actually, in general, we can put the forces into three different categories. But compared to the first two terms, the drag forces from friction is always very small. So in our case, we usually just ignore the last term, and we consider the pressure, we consider the acceleration force from added mass. And in this slide, you can see
differentiate DUDT, why else they have been signed instead of plus?
we
The DUDT for this AX, acceleration in the X direction. When we differentiate the U, I don't see an exams here.
Here the expression, because in this table you don't have the expression for vertical part, the vertical components, so that's why I give you the expression here. Yeah. But for the horizontal velocity and acceleration, you can just get them from the table. Yeah.
This acceleration is
Can you use that table, please? Okay. In this slide, we can see different expressions. The first one, it's for pressure force, but it's very, very theoretical because from the table you can see that the dynamic part is rho kt square r not r2 square h. Because the static part will give you the buoyancy only, so you don't have any motions. But this part will generate motion. But we should do some change, because we know that in deep water, when the water depth D is a great value, we have this, right? And then that's the reason why the expression will be in this way. Okay? And if we write the expression in another way, you can see that here is the frequency, right? And then it's wave height, okay, omega square is cosine. Here is kg, right? Here is the reason why you can see the expression here for integration, right? That is pressure. We have rho, we have g, we have h, we have 2, we have this term, we have our cosine function. And then here is the pressure for one point, and then if you do an integration for the whole surface, we will have the total pressure from water, from wave. Okay? But actually in our estimation, we don't use this one. Okay? We use another way, that is F is MA. That's the reason why we need to know AX for surge or AZ for heave. Okay? And M we divide into two parts, the real M of your structure and the added mass because of your motion. And then, here's your force. Because when you use the mass or the weight for your structure, we will have an additional part. That's why we define another constant to show you the part is big or not. And we call that added mass coefficient. And then maybe you can use another coefficient, but the value will be 1 plus the coefficient for added mass. So that's why sometimes you can see this. When you use the mass, we use the coefficient multiplied by real mass of your structure.
So basically M is the one you're going to multiply with your AZ or probably AX.
Yes, that's the mass you need to use. So see, if we do an integration in this way, we will have the mass, right? You have the cross-sectional area, you have density, and here is for a small element, and we do the integration for the whole length for the displacement volume, right? You have the total mass for calculation. If I use the acceleration. Actually, it's MA. And then here is force. That's the basis for your estimation. So if focused on the structure, we can define natural frequency for your structure. We need a capital K, we need the real mass, we need your added mass. And for the stiffness, we have another definition to define, that is rho g and the cross-sectional area at the waterline surface. And from the table, you can see the expression for the motion induced by wave. So when you need the wave response, you need to define the maximum force. You need to define the natural frequency. The stiffness and natural frequency. So after you have the values for them, you can estimate what is your maximum motion. And you can find all of them from the table. CA?
Yeah, coefficient of added mass equals to 1 plus this one here.
It's for added mass coefficient and if just focused on the value, it should be the added mass over the real mass of your structure. Okay? So that's the reason why MA is CA multiplied by M. And then for your calculation, it should be M plus MA. Right? And in your equation tables, I think you can also see some triangle functions, like the 4 items in this slide. And sometimes you need to use them to combine different terms, because in some terms we have a sine function or cosine function. After the theoretical basis, I have two examples in this slide. But I think it's better to do the practice before I go through the two examples, right? So I hope I can do this in the revision week, so you can check your calculation. Yes, I will upload right now. Yeah.
Question. Can we ask one question?
Okay, wait a minute. And in these slides, I show you some key steps for the final solution, and I think you can use them as a reference for your calculation. If you cannot follow them, I will do that for you in the last week before your exam. But anyway, if you have any questions, you can just go to my office. Yeah, anytime. I should be there the most time.
Example one, please.
Example what? This one?
No, this is two. Example one. Is it here? No.
For lecture 5 and 6, sample 1, 2.
Lecture 5.
Yeah. That one. Sure.
Why you are using? You are going to find wave execution force, but you are using only one integral there, not two integrals from the formula. Why you are using one integral here?
This is wave excitation force in two directions.
You want to know why we use only one integration, right? Because previously, according to the theoretical basis, we should do the integration for the whole surface, the total surface area for the structure. But actually, because it's horizontal one and the diameter is quite small, so we assume that the water particles acceleration on the whole height, we can use only one value, because it will simplify our estimation. So if we assume that we have only one acceleration, which means if we can find what is m, we will know what is f, right? So here is the mass for where's the ideal mass? Oh, this example is wrong.
They all the same calculation. Both force.
No, it's wrong because I lost the ideal mass. It's not because of the integration.
No, I'm not saying about the integration, but the thing is here in the formula,
Yeah?
for the wave excitation force, there is two integrals even, but in calculation there is only one.
Because we use another way. We don't do integration for the whole total surface.
For the another structure also.
Yeah, because from this way you can estimate the mass already.
Yeah.
Yeah? So you can apply the F is MA. You don't integrate all the points. Do you know what I mean? Okay, come to me after lecture. Thank you. I will change this example because I lost the ideal mass term.
The second question is, this is 1.025, not 1,000, right?
That is density of C delta.
The
1.025. Density of C delta.
I think we use kilonewton, so should be correct. But anyway, I will change this one because I lost the term. But about the integration, I think it's correct because we use another way to do the estimation. We don't integrate all the pressure at different points on the total surface.
No, here in the wave excitation, here is given the K forces, and you just add the next one, the search force. For the structure, you have here two forces.
Yeah. But now, the question is to get the heave. Here it's for two directions. You know what I mean?
Yeah. But the second, not this one, I think second one or third one, there was one question for the wave excitation.
Second one?
Second or third one, I've seen somewhere. There was one missing force.
Oh, really?
Yeah.
But I think I have checked them already. Should be correct. How about this? I go back and go through all of them, and then I will send you guys again. Because I got the materials from Professor Longmin, and to some of the equations, I don't have the equation tool to edit them. So some of them I can't change. I can only create a new one.
Okay. Well, thanks.
So I think I can stop here, and I will ask our timetable service to move the 2 hours on this Friday to the revision week, and in that 2 hours I will show you one step by one step about how to go through all the examples here. Okay? But I think if I was right, as example 1, it should be the only one with some wrong. All the other things I have followed them already to get very similar solutions.
So I have a question, sir. When marking in exam, when you mark it, you actually use it for the final answer, or you're looking at step by step?
No, yeah. For every step, you will get 2 or 3 marks. So it doesn't matter if you don't have a good final solution. Yeah. Of course, yeah. Is there any project that relates to something like the use of plastic, thermoplastic pipe for the SJ and JMA? Do you have any project like that? You want to focus in the flow or the fatigue things? Fatigue things, no. In my area, I don't do simulations for structure fatigue. But I think you can go to Yongchang.
Who's that? Do you have his email address?
I show you. 用上严重
I'm
and
thinking of doing something on static analysis of thermoplastic.
I'll show you.
Dr. Pu.
Yeah.
Oh, Dr. Pu, right? Yeah, he's teaching structural analysis. Okay.
So
I already sent him a mail.
no, go to his office
Okay.
because he's very busy.
Okay.
Yeah, probably every day he has more than 20 emails. He can't reply everyone.
No, he replied that he's going to contact me later and fix me up with whatever is involved. So, but maybe I should go and see him personally.
I think it's better. Yeah. Just not to talk to him.
Can I have a discussion with you about the? Well, I want to know my research, not my research, my dissertation is talking about the pipeline doing Chile or Asle. The force, I mean the dynamic force goes to the pipeline. Can we have a discussion on that? I mean, I can email you personally.
Yeah, of course. You can go to my office later.
Okay, yes, I can email you personally.
Please, I want to ask something about the stiffness. This, when we use stiffness, is equal to K. K is we use the area AW.
Yeah.
Right? So why are we using the area of the upper structure?
Oh, that is because
That's the restoring force.
that is because when you have right? It's like you are connected to the force is from this part, and this part is and you have the buoyancy that's only for the what about this one? Because this is the buoyancy, you are always underwater. You have no buoyancy chance. The response. Every action there is and the only change is your job. And when you estimate the buoyancy, you need the it's like you have a screen. So that's a reason why we call that stiffness. The other case is just for few motion, up and down.
Something when you talked about the slugging, yeah, the project, slugging in subsea aspects. I was thinking of something to do with the flow assurance,
Yeah.
but flow assurance with regard to wax oil.
But slugging, slugging is only one point in flow assurance. You may have many, it's a big area.
Yeah.
And when you estimate the reliability, it's slugging is only one item in your list.
Okay.
So if you want to focus on the slugging, it's fine. But if you talk about the flow assurance, slugging should be only one part.
All right. Okay. Let me think about it.
And in our school, we Professor Longbin has just has PhD students graduate, and his topic is focused on reliability of the subsea systems. So I think you can talk to Professor Longbin. And the guy just graduated from our school, is from Nigeria.
Okay.
Okay.
All right. Okay. Okay. I'll check it. Thank you.
Thanks.
Sorry, regarding the forcing, when we calculate this wave excitation force, for example, submerged object like that one.
Yeah.
So, in this example, we were asking about heat force, but the same is there. We have formula for the excitation force, which is heat force and the surge force, not added together.
Yeah.
So in this situation, what kind of, wave excitation force is it?
It should be a combination.
Combination of heat and the wave or current effect, or what's it?
It should be a combination of the forces from three directions.
Three directions.
And in our table, you can see the expression for heave, the expression for surge, but actually we should have expression for sway. So when we say the exception and force, it should be a combination of the three.
But there is two.
Because we can only assume we have two, otherwise we can't finish the estimation.
Okay.
If you assume the wave is like this, it's a two-dimensional.
Yeah.
You don't have space wave. You have only two directions. That's the
So
reason why they have only two expressions in that table.
okay. Okay.
But we know that if in a real case we may have many waves together and they have different directions. So obviously you have coordinate systems like this. So it should be a combination of the forces from the three ways.
Okay, thanks.
Please. Yes. Can we put one of the examples? Like this example. No, not this. We're given this. Is this part of the question? We're given this. Is that the reason why we divide it into two? Like the wave. We're given this wave starting here. Is it possible that they draw the diagram to be?
Sorry, I didn't get you.
The reason why they always divide the length into two. Why?
Divide the length into
divided by two during the
I mean minus.
Integration. Yeah, minus.
I mean minus. No, it's fine. If you do integration from 0 to L, you will have the same thing.
The whole length.
Yeah, it's just for the whole length. But no matter how do you define the original point.
Okay, so basically when we have a structure, we just divide into two to get the whole integration.
It's not necessary. If you put the structure here to here, you will have the same solution.
It'll be the same solution.
Yeah.
Okay.
Yeah.
Then sorry, there's an example. I was trying to get the forces, pontoon and acceleration. Oh yes. Yes. This at the end of the day is like times the force on the pontoon. We have
pontoon pressure plus pontoon acceleration, but they are the same.
No, it's from the dynamic pressure. It's from the particle acceleration. Yeah.
But they're the same in this particular.
Yeah, because from the if you have that table, you can see that in this case the added mass will be exactly the same like the real mass. So that's the reason why just double 2. Yeah.
Okay.
Yeah. You can get this from that table. Yeah.
Okay.
All right. Thank you.
Thank you.
No problem.
Grazie.